Welcome to the 15th lecture from chapter number 8. We are studying VLSI design and we will continue studying logical effort. Today we are going to solve a problem to revise whatever we have studied in logical effort. A process is given where the ratio R is given to be 2.5, the mobility ratio is given to be 2.5, and we have to find out different quantities for this chain. The first quantity that we are required to find is the path logical effort G, and we know that this is the product of individual logic efforts of each gate. Here in this chain we have 4 gates, so it would be 4, or it would be G1 times G2 times G3 times G4. So what is the logical effort for the first gate? It's a 3-input NAND. We know that for a 2-input NAND, G for NAND 2 we studied that this is R plus 2 over R plus 1, and then we studied, it's a small recap of what we have been studying, and for NAND n, G is R plus n. Therefore for NAND 3 this would be R plus 3 over R plus n or R plus 1. So this is R plus 3 over R plus 1. Second gate is NAND 2. This is, we already know, R plus 2 over R plus 1. And we have studied that for NOR gates, for a 2-input NOR, this is 2R plus 1 over R plus 1. This we have proved in our previous lectures. And for an n-input NOR, this is n times R. And for a gate, and for a NOT that is symmetric and m is equal to 1, this is 1. So if we plug these values in, we can find capital G, that is R is 2.5, 2.5 plus 3 is 5.5 over 3.5. R plus 1 would be 3.5. And then G2 R plus 2, it is 4.5 over 3.5. 2R is 2.5 times 2, 5 plus 1, 6 over 3.5 times 1. This comes out to be 3 point something, 4.46. And we know that the path electrical effort capital H is 1 to 4 HIs, and we already know that this is H of CL for last gate divided by H of Cin of first gate. All the terms cancel, we have already studied that. So H comes out to be CL, the load capacitance of the final gate, divided by the input capacitance of the first gate, CL over 10. So it comes out to be a 10. So now we have computed G, we have computed H, and then now we are ready to compute the path effort. The path effort is the product of logical effort and the electrical effort. We already know G times H. 3.4 times 10 is 34. And then this is the path logical effort of the chain. And what is the average path logical effort? What is the average path effort of each gate? This is approximated as F to the 1 over n. This F and n is the number of stages. So here we have 34.6 to the 1 over 4. It comes out to be 2.43. Lastly, we have to compute H of each gate. What is the input capacitance of each gate? The input capacitance here, let's call it C4. The input capacitance here C3. The input capacitance C2, and the input capacitance here, let's call it C1. How to find the input capacitance of each gate? For the first gate, that is a NOT, H of this gate, this is gate number 4, this is gate number 3, 2 and 1. For the fourth gate, we know that F is G times H. So if it is 4 and this is the average, this means this can be applied to any gate. Since this is an average, this is true for all these 4 gates. So this would be F over G4. So F over G4, F is 2.43 over G4. G4, what was G4? G4 was R plus 1 over R plus 1. It's 1. We have just computed in the long expression that we wrote for capital G. The last item in that expression is G4. You can go back and verify it's 1. And this is also the ratio between, we already know that the electrical effort is the ratio. Electrical effort of a gate is the ratio between its output and input capacitance, CL over C4. And we know that CL is 10C. It's 10C. So now we have only one variable. It's 2.43 over 1 means 2.43, and C4 is 10C divided by 2.43. So C4 is 4.12 times the reference capacitance, that is the input capacitance of the first gate. Then we have to compute this capacitance, the capacitance C3. For that, we will get help from H, which is the electrical effort of the gate, F over G3. So F is 2.43 over G3. G3 was computed by us as 6 over 3.5. In the long expression that we wrote for capital G, we can verify it's 6 over 3.5, and it can also be written as the output capacitance of the gate divided by its input capacitance, that is C4 over C3, and we already know C4 is 4.12 times C. 4.12 times C. So now we have only one variable in this equation which we can solve for, and we reach to an answer 2.91 times the reference capacitance. So for this, the aspect ratio would be different. For this gate, the aspect ratio would be different because the input capacitances are different, and input capacitance we know is directly proportional to the aspect ratio. For C2, we'll write an expression of H, electrical effort, for this gate number 2. This is F over G2. F is the same, the average path effort divided by G2, and we wrote G2 to be 4.5 over 3.5 in that long expression that we wrote for G, and this must be equal to the output capacitance of the gate divided by its input capacitance C2, and we know that C3 is 2.91 times C. So solving this gives us C2 is equal to 1.54 times C. Finally, we move on to the first gate as the last item of this lecture. The first gate, electrical effort for the first gate is H1, which is equal to F over its G. F is the average divided by the G. Divided by the G. G is G for this gate. We wrote in that long expression 4.5 over 3.5, which is equal to the output C2 over C1, and we know that C2 is 1.54 C. So C1 comes out to be C. You can verify C1 comes out to be C. So we will keep on studying gate delays in our upcoming lectures. Thank you.